Our topic this week is sampling, that is, producing samples from some probability distribution such that we produce a given sample with a frequency that's proportional to its probability. So there's two reasons we might be interested in doing sampling. The first is sampling for its own sake. So there are a lot of applications that require one to sample from a probability distribution. Some examples include producing test cases, so producing test data to test, for example, some machine learning method, or really any algorithm. It's very common to want to, create test data from some distribution and see how a given algorithm performs in practice, or even some physical system that one is developing. Other applications that want sampling include like various kinds of art. For example, one might want to make a background for some image of a beautiful forest or a town or a level for a video game. All those things might involve sampling from some distribution. The other application, the reason we would want to use sampling is it turns out sampling is often an extremely effective method for approximate probabilistic inference. So I mentioned last week we were talking about exact probabilistic inference, and that problem is hard in general, and there are many probability distributions for which we'd like to be able to do probabilistic inference that we can't, that doing it would require exponential time for some very high exponent. And so when that's the case, generally we need to resort to approximate inference. There are generally two big classes of approximate inference methods. The first is variational inference, and the second is sampling-based inference, particularly Markov chain Monte Carlo, which is the main algorithm that we're going to talk about this week. We don't have time to talk about variational inference in any depth, unfortunately. I think I'll briefly discuss it in the bonus topics next week. But what we are going to talk about is sampling-based inference, and in particular, Gibbs sampling and Markov chain Monte Carlo. Let's start with looking at how to sample from a 1D distribution. So let's say we have some probability distribution that we want to sample from, where x is a 1D value, just a single input. We'll talk about multivariate sampling, where x is a vector, in a little bit. So first, let's define f of x as the CDF, the cumulative distribution function of f of x. Here they're drawn here. Remember that the cumulative distribution function is just the integral of our initial probability distribution. Then let's define f inverse of f of x. And let's use a different value. Remember that the inverse of a function is f inverse of u equals x if f of x equals u. Okay? So now note that a function only has an inverse if it's a one-to-one function. That is, each input produces a unique output. And unfortunately, that's always the case for a CDF, right? Because it's an integral, you can only add up the numbers as you go on the horizontal axis. So a function that looks like this, say, doesn't necessarily have an inverse, because the same or two different inputs can give you the same output, but a CDF will always have an inverse. Okay, so f inverse of u is the inverse function of our CDF. Now, to sample from this function that we're interested in, first we're going to generate a value u according to the uniform distribution between 0 and 1, and then plug u into f inverse. And it's not too hard to see that doing so will give you a value that's distributed or that will sample exactly from p of x. So some way to get a sense of this intuitively is, well, first thing, what does it mean to take u and put it through the inverse function? One way to think about it is to look at this CDF plot. We randomly pick a value between 0 and 1. Note that the CDF will always be between 0 and 1 because p of x has to sum to 1. We find u on the vertical axis, and then we follow it horizontally until we get to the corresponding point on f, and then follow that down to get to the corresponding input. So just to get some intuition about this, for values that have high probability net density, that's going to correspond to high slope positions on the CDF, which means that in some sense, there's kind of a big range of u that's going to give us those high slope positions. And then, for example, for very rare, very low likelihood values, there's very few values of the uniform distribution that will give us this. Okay, so this is a way where we can sample from a 1D distribution. So, for example, if you want to sample from a normal distribution or exponential distribution or anything like that, that's how we can do it. Note that we've assumed that we have access to the uniform distribution. That's implemented on most kind of operating systems, usually using a pseudo-random number generator. We're not going to talk about random number generators here. We're just going to assume that they give us a value that's distributed as close to uniform as we need it to be. Okay, let's do an example. Let's say we want to sample from the exponential distribution. So that is a distribution with a density defined like this, lambda e to the minus lambda x. So lambda is kind of our shape parameter for the exponential distribution, and x is the thing we're taking the density over. The exponential distribution looks something like this, where it has high values for values close to 0 and low values elsewhere. Note that it's only defined on positive values of x. Okay, first thing we need to do is we need to take the integral. So we take the integral of this thing from 0 to a particular value u, let's call it. If you do this integral, I'm not going to do it out explicitly, but we get this thing. By the way, I'm including this indicator function here. This is just to show that this is defined only for positive values of x. Okay, so if you do the integral, you get this. It's not too hard to do. So that's our cumulative distribution function. Now we need to take the inverse. So to do that, let's say we call this y, and then we solve for x. We're going to get x as a function of y. Again, I'm not going to do this explicitly. Take the 1 and put it on the other side, take the log of both sides. We get this thing. I encourage you to do the algebra and double check this. this is the inverse function of this. Okay, and now we're done. So anytime I want to sample from the exponential distribution, I take and I draw a value u from the uniform distribution from 0 to 1, and then I take f minus 1 of u, and this thing is going to be my sample that's distributed according to the exponential distribution. By the way, we are talking so far about continuous 1D distributions. I should say that it's extremely easy to sample from a discrete distribution. Okay, if I want to do that, I just, let's say I have 5 probability values, probability of x1, probability of x2, ... I just sample from the uniform distribution and ask if it's between 0 and p of x1, then I output x1. If it's between p of x1 and p of x1 plus x2, then I output p of x2, and so on. This is probably also implemented, Python, even in the default random package, doesn't have a distribution function for kind of all of the more sophisticated distributions, but it has this one. If you just give it a distribution and ask for a discrete value distributed according to that distribution, it can give it to you, and that's how it's doing it. By the way, you can think of this in the same way as this inverse CDF version. So what does the CDF look like for a discrete distribution? It looks something like this. Let's say x3 has much higher probability than the other two. Well, if I want to sample from this distribution, well, I just take a uniform value between 0 and 1, and then again, plug it into that inverse value. So either way you think about it, thinking about it this way gives you exactly the same solution as if you think about it this way. Both perfectly valid and very extremely easy ways to sample from a discrete 1D distribution. Okay, so that strategy, sampling by plugging into the inverse CDF, is great, very efficient, but it requires that we be able to, one, take the integral of our probability density function in order to get the cumulative density function, and we have to take the inverse of that cumulative density function. Now, both of those are well-defined mathematically, but we might not be able to do that analytically. So what if we can't do that analytically for some distribution that we're interested in sampling from? Well, in that case, we can use what's called rejection sampling. Okay, let's do an example. Let's say we want to sample from the exponential distribution. So that is a distribution with a density defined like this, lambda e to the minus lambda x. So lambda is kind of our shape parameter for the exponential distribution, and x is the thing we're taking the density over. The exponential distribution looks something like this, where it has high values for values close to 0 and low values elsewhere. Note that it's only defined on positive values of x. Okay, first thing we need to do is we need to take the integral. So we take the integral of this thing from 0 to a particular value u, let's call it. If you do this integral, I'm not going to do it out explicitly, but we get this thing. By the way, I'm including this indicator function here. This is just to show that this is defined only for positive values of x. Okay, so if you do the integral, you get this. It's not too hard to do. So that's our cumulative distribution function. Now we need to take the inverse. So to do that, let's say we call this y, and then we solve for x. We're going to get x as a function of y. Again, I'm not going to do this explicitly. Take the 1 and put it on the other side, take the log of both sides. We get this thing. I encourage you to do the algebra and double check this. This is the inverse function of this. Okay, and now we're done. So anytime I want to sample from the exponential distribution, I take and I draw a value u from the uniform distribution from 0 to 1, and then I take f minus 1 of u, and this thing is going to be my sample that's distributed according to the exponential distribution. By the way, we are talking so far about continuous 1D distributions. I should say that it's extremely easy to sample from a discrete distribution. Okay, if I want to do that, let's say I have 5 probability values, probability of x1, probability of x2, ... I just sample from the uniform distribution and ask if it's between 0 and p of x1, then I output x1. If it's between p of x1 and p of x1 plus x2, then I output p of x2, and so on. This is probably also implemented, Python, even in the default random package, doesn't have a distribution function for kind of all of the more sophisticated distributions, but it has this one. If you just give it a distribution and ask for a discrete value distributed according to that distribution, it can give it to you, and that's how it's doing it. By the way, you can think of this in the same way as this inverse CDF version. So what does the CDF look like for a discrete distribution? It looks something like this. Let's say x3 has much higher probability than the other two. Well, if I want to sample from this distribution, well, I just take a uniform value between 0 and 1, and then again, plug it into that inverse value. So either way you think about it, thinking about it this way gives you exactly the same solution as if you think about it this way. Both perfectly valid and very extremely easy ways to sample from a discrete 1D distribution. Okay, so that strategy, sampling by plugging into the inverse CDF, is great, very efficient, but it requires that we be able to, one, take the integral of our probability density function in order to get the cumulative density function, and we have to take the inverse of that cumulative density function. Now, both of those are well-defined mathematically, but we might not be able to do that analytically. So what if we can't do that analytically for some distribution that we're interested in sampling from? Well, in that case, we can use what's called rejection sampling. Here's what we do in rejection sampling. So P of x is going to be the distribution that we want to sample from. By the way, we're using P tilde of x to mean that this can work even if we don't know the normalization constant. That is, using P tilde of x as the unnormalized distribution. And we've talked about there are a lot of cases, particularly in the cases where there's evidence or unobserved hidden values that we don't care about, where we might not know the normalization constant. So P of X is the distribution we want to sample from. We're going to sample from some other distribution, Q of X. This is called the proposal distribution. We would like Q of X to be something similar to P of X, not too different. I'll talk about why we would want to do this, but this works in general for any proposal distribution. So let's just say we have some proposal distribution Q of X. The only requirement is that the domain of Q of X has to equal the domain of P of X. So if there's any value in, or at least the domain of Q of X has to be a superset of the domain of Q of X. So it has to be the case that any value that P could produce that has non-zero value, non-zero probability according to P of X has to have non-zero value, non-zero probability according to Q of X. So we're going to generate X according to Q of X. So generally we're going to do that using the inverse CDF method. So we're going to choose Q of X to be some distribution where we can analytically find the CDF and take its inverse, and therefore use the much faster inverse CDF method to generate X according to Q of X. Then we're going to do the following. We're going to define M, where M is some constant such that for all X, M of Q of X is greater than or equal to P of X. So, for example, if Q of X is the uniform distribution, by the way, the uniform distribution is also a common proposal distribution. And of course, we don't have to do anything fancy to do that. We're assuming that we can sample from the uniform distribution. Then M would be the maximum value of P of X. I'll give a kind of a graphical explanation of this in just a minute. Okay, so we've defined this value, so we just have to figure out some value of M that such that this inequality is satisfied. Then we're going to sample another value, U, from the uniform distribution. And then we're going to ask, is P of X over MQ of X, is that greater than U? If it is, we keep that as our sample. If it's not, we throw away our sample and start over. And we keep going until we get a sample that we accept. Okay, let's give kind of a graphical explanation of this. So let's say we want to sample from this shaded distribution here. Let's call this P of X. And we're going to sample from this thing here, which is a Gaussian distribution. The Gaussian distribution is going to be our Q of X. Graphically, we can think of it kind of like this. We reject anything in this region here. We throw those samples away, and we end up with just these samples. So let's look at what that looks like here. Let's say we sampled this value of X according to Q of X. Actually, use a slightly different one so we can see the difference between the two distributions here. So here's our X. And here is MQ of X. Notice that if I hadn't multiplied by M, the Gaussian distribution would look probably something like this, where there'd be some values that were lower. So that's not allowed. So we've chosen M such that this MQ of X curve goes always above P of X. This is going to be a hand-wavy proof, and then we're going to do a formal proof in just a second. So now here's the X that's sampled from Q of X. Now I'm going to ask, what is P of x over M Q of x? So notice that M Q of x here is high, and P of x is somewhat lower than that. Looks like about half in this case. So this thing in this case is going to be about half. If we had sampled this point, it would be close to 1. If we had sampled, let's say, this point, it would be close to 0. Then we're going to accept if u is less than, in this case, 1/2. So you'll see that in cases where P of x over MQ of x is high, then we almost always accept, and cases where it's low, we almost never accept. Okay, so this is the idea. Again, what we're trying to do is we're sampling from MQ of x and then throwing away samples such that we can sample from P of x instead. So this is a way to get around having to derive the CDF and the inverse CDF, and instead we can use just P of x. Okay, why is this the right thing to do? So this picture is kind of the hand-wavy proof. I'm going to do a slightly more rigorous proof. So what is the probability that we output a particular value of x? I'm using P apostrophe to indicate the sampling process. So we would like it to be the case that P apostrophe of x equals P of x. So what is P apostrophe of x? It's probability that we sample x and accept divided by the probability that we accept overall, that we accept anything, because here we're sort of implicitly conditioning on the fact that we have output something, and that thing we've output is x. So in the denominator goes the overall probability that we accept. So let's figure out what this is. The probability that we sample x is just Q of x, and the probability that we accept that sample is P tilde of x over M Q of x. Now, what's the probability that we accept overall? Well, to get that, we have to do the integral over all the possible values of x. I'll use x prime of this thing at the top. But here, note that and that would be a very hard integral to do, except that we can notice first thing that Q of x cancels here. So we just get P tilde of x over M. Now this thing on the bottom equals just z, which is the normalization constant of P of x divided by M. So we can get rid of that whole thing. Our m's cancel. So our solution is 1 over z P tilde of x, which is exactly the distribution we wanted to cancel to sample from. Good. So this says that rejection sampling is letting us sample, in fact, from the correct distribution. So rejection sampling works, and generally it's much easier to derive than the inverse CDF method, because notice we just need two things. First, we need to define our probability density function. We don't even have to normalize it. And two, this is the slightly trickier part, we need to find M such that this relationship holds. Usually that's not too hard. We just have to somehow be able to put some upper bound on the value of P of x, and in particular, an upper bound on this ratio P of x over Q of x. If we can do that, we can use rejection sampling. What's the running time of rejection sampling? On average, it will be 1 over the accept probability. At least that's the number of times we need to sample. Let's assume that this sampling step is a constant time operation. So our running time is proportional to our accept probability. What is our accept probability? It turns out it equals roughly z over m, where z, again, is the normalization constant for P of x. So if we have an already normalized distribution, then z is 1, and our acceptance probability is 1 over m. So that says that we want a proposal distribution such that we can choose m as small as possible. If we can choose m that's small, let's say 2 or 10 or something like this is no problem. If we have to choose m that's 1,000,000 or something like that, well, our running time again is 1 over the acceptance probability, which is to say it's O of m. So we want to pick a proposal distribution, again, that's pretty close to our target distribution, so that we can choose m that's reasonably small, so that rejection sampling is going to run reasonably quickly. Let's do an example. The example we're going to use is the gamma distribution. So recall that the gamma distribution, why might we want to sample from the gamma distribution? It's the conjugate prior to a lot of distributions that we use very often. For example, a normal distribution or Poisson distribution. So a gamma distribution is something we'd very much like to be able to sample from. For example, because if we want to use it as a prior for, let's say, a Gaussian distribution, then we might want to initialize some parameters, and we probably want to initialize those according to a gamma distribution. Okay, so we're going to use rejection sampling to do that. So there's one trick that we can use. If we take x and we sample it according to the exponential distribution with some parameter lambda, and we do that k times and add those all together, it turns out, this is not too hard to prove, I'm not going to prove it here, that if you do that, y is distributed according to gamma of k lambda. The definition of the gamma distribution, I'm not going to repeat it here, but remember that gamma distribution is a distribution that has these two parameters here. The definition is written here. Okay, so gamma has these two parameters. If we sample x according to the exponential distribution with lambda, add those together, then y is sampled from a gamma distribution with k lambda. And note that we can use the inverse CDF method to sample from the exponential distribution. We showed that in our previous example. So that's great. We don't need any more work, any rejection sampling or anything, as long as k is an integer. Okay, but what if k is not an integer? So instead, let's assume we want to generate according to a gamma distribution with parameters alpha and lambda, where alpha is not necessarily an integer. Well, let's use the following proposal distribution. And we've chosen this proposal distribution because we're going to find that it's not too hard to identify a value of m that satisfies that criterion that we want, that gives a maximum to P of x over Q of x. So this Q of x that we're going to use is this thing here, gamma of k, where we're defining k equals the floor of alpha. Recall that the floor is the largest integer less than alpha. So for example, if alpha is 5.5, then we choose k to be 5. That's our first parameter, floor of alpha. The second is lambda minus 1. Okay, so we need to put a bound on p of x over q of x to use as m. Let's figure out what that is. Okay, so let's write out both our top and bottom expressions. On the top, we have x to the alpha minus 1, lambda alpha, x above minus lambda x over the gamma function of alpha. Recall that the gamma function is equal to the gamma function of k equals k minus 1 factorial. And the gamma function is essentially a continuous extension to the factorial function. Okay, so then we have the same thing on the bottom. We're just plugging in our values to the definition of the gamma function. Let's do some algebra. We have x to the alpha minus 1 on the top, x to the k minus 1. So we get just x to the alpha minus k. We have x of lambda x on the top, sorry, negative lambda x on the top, and x of negative lambda minus 1 of x. This becomes minus lambda x plus x. So these two cancel each other, and we just get x of positive x on the bottom. That goes to the top to become x of negative x. Then we have our two gamma distributions here. They stay, and we have our lambda to the alpha and lambda minus 1 to the k here. Now, so we need to put a bound on this expression. This is not too easy. I'm not going to do the algebra here. It involves figuring out the maximum of this ratio, which admittedly is kind of non-trivial. But it turns out that if you do that, one way to do it would be to take the derivative of the top and bottom, set it to 0. That's going to give you the maximum. If you do that, you find that the maximum of this thing equals alpha minus k. And recall that alpha is the floor of k. Oops, sorry, k is the floor of alpha. So this is essentially just the non-integer part of alpha. So if alpha is, say, 5.1, then this thing is just 1. If it's 5.8, then this thing is 0.8. That means we need to define m to be gamma of alpha minus k alpha lambda divided by gamma alpha minus k lambda minus 1. Okay, so this is the maximum ratio between the two. So with a little bit of work, we found m. This is just going to be some constant value. Now, to sample from our particular gamma distribution that we want, we sample instead from this gamma distribution using this sum of exponential distributions trick. Then we use the rejection sampling method that we showed before to reject each sample with some probability.